everyone. Sorry about the technical difficulties that we keep experiencing. I think we're ready to go now.
Sure.
So what we're going to do before we actually go into climate science and what it all means, we're just going to look a little bit about some of the sort of psychological reactions we tend to have to difficult information. And I think if any of you, perhaps like me, have experienced trying to talk to people about climate science or what's going on, and you often sort of have this lights out moment where people just don't want to hear anymore. And I just thought actually that might be a hopeful place for us to start, just to kind of think about how we talk about this and perhaps how we might also react ourselves. So I'm just going to talk about this a little bit as well. This is the model that I met with, so one of our trustees took me to see a very an elderly gentleman who's a psychotherapist, been working in lots of different interesting areas. And we were talking to him about this project and some of the challenges that we face. And he started explaining to me what he described as the anxiety gradient, which I've tried to represent on this chart. And so, if you think about the, ultimately, there's depending on the information we're dealing with, there might be a rising level of anxiety. And for most people, there is some point along that gradient where you have almost a lights out moment. And so, one of the things he said, which I thought was quite interesting, and I have to say, from when I maybe first sort of shared some of the information I'm going to present to you with my friends, maybe sort of 6 months ago, they kind of got the unrefined version. What he actually also said was, if you're going to take people along this journey, which might lead to rising anxiety and maybe even fear, it really does help if you've actually got something practical and useful that you can kind of point them towards to do. And for those of you who've been involved in the Extinction rebellion, I mean, it's very much a tactic. It's, let's tell people quite where we're at, and then let's see if they want to get involved with doing something. I guess that was just to mention that. And then, Joseph, do you want to maybe talk about the next slide?
So this is a similar system map, and this is what I find really helpful. So basically, you have these 3 areas. So you have freeze, the window of tolerance, and fight and flight. Thank you, Sam. Just feel free to move me back. So, you can see from over here. Oh, right. So basically, what you have is that, so the freeze is, if you think of it, it's kind of like numbness or apathy. It's like you're just kind of below a level, the information isn't hitting you, it's just like you don't want to hear it. And then on the other side of it is the kind of panic. It's just like lights out, just like, total, like too much overwhelm. And then between them you have this point of window of tolerance. It's kind of like, you can almost think of it like a bike point on a car. If you're revving too much, if you're just firing information, it just goes over the top of people's heads. And equally, if people aren't engaged, if you're not able to kind of bring people up to a place of engagement, then it's not going in either. And actually what's interesting is that this window of tolerance, it can change, it can move. So if you're coming straight off the street and you're busy, the window of tolerance is very, very small. Which is why we started with this story. It's just this kind of way of just landing in the body. And actually embodiment is the greatest, the most effective way of being in that window of tolerance. So throughout Sam's talk, especially, where we're looking at kind of the more difficult information, just like really inviting you to just every now and again just check in with your body, see if you're like tensing up or anything like that. Just like take a deep breath. It's like to kind of not just go into overdrive, but it's just to keep coming back into a more centered state. And so also then if you're speaking to someone about these issues, and either they're in this kind of numb place, if you fire information at them, it's not going to do anything at all. It's just not going to hit them. And if people are going into the kind of panicky space, the more information you're firing at them again, actually the more panicky you're making them. So it's about how to bring this equilibrium where people are actually receptive to hear what you're saying. And I'll be talking a bit more about that in the section afterwards, about just some helpful framework to kind of be in that place of being receptive.
All right, thanks very much. So this is a presentation that is adapted from one I gave to, it's actually a part of a webinar, mainly for institutional investors back in October, November. And really what it's trying to do is summarise, I guess, my understanding of the climate change issue, and also just sort of some of the recent developments that I think are important to know and to understand. so let's start at the beginning. What actually is this all about? Well, it's the greenhouse effect, which we've actually known about since 1896. So, if anyone tries to tell you it doesn't exist or whatever, we've known about it for a long time. And very simply, we have energy coming in from the sun, it gets trapped within our atmosphere, and our planet warms up. Some of it gets reflected back out into space, and essentially it's greenhouse gases, which we'll explore in a moment, that are trapping that heat and leads to the temperature that we have on Earth. It's a pretty well understood process. You can replicate it using things like greenhouses, and then. So, next thing to mention then, sort of 101 in terms of carbon, is that we have the Kyoto basket of 6 greenhouse gases that are all essentially warming gases. And because carbon is the most prevalent, we express them as in terms of carbon dioxide equivalent. So this table, don't worry, I don't have to memorise all of this, but it just gives you sort of an overview: carbon dioxide, methane, nitrous dioxide. I'm not even going to try and pronounce the others, but they're the ones that, if you look over to these 2 columns, so global warming potential of carbon is 1, and all the others are expressed in terms of carbon. So what that means, for example, nitrous dioxide, is that is 264 times more powerful than carbon. And what's interesting when you look at this is that they have different time horizons. So unfortunately, when we put these things up into the atmosphere, they stay there for a very long time. Some longer than others. But if you look at methane, so its global warming potential over a 100-year period is around about 30 times. This is taken, by the way, from the IPCC, I think it's the 5th annual assessment report. It's peer-reviewed. There's different numbers that pop up in different places, but this is pretty much the latest data that you can get. But then when you look over just a 20-year period, it's quite considerably higher, so 84 times higher. Whether it's 80 or 85, it doesn't really make much difference. It's a more powerful gas. And then you see these other ones here, and a lot of those appear in things like fridges, for example. So if you look at the Drawdown initiative, which is essentially documenting all these various different things we can do to actually draw down carbon that we've put out there, you'll see that refrigerant management is quite high up. And I'm pretty sure that's because there are these various gases in those fridges. So that's just to kind of set the scene. So let's just look at some of the recent news over what I would say really the last, what are we now, we're June, so the last year and a half, where I think things might have accelerated somewhat. So the first would be that we've seen wildfires pretty much all over the place, places like Japan that don't typically have wildfires, Lancashire, which certainly closer to home for us here in the UK, but perhaps most worrying, places like Siberia or even Sweden, where effectively the Arctic was on fire last year. They even had to borrow a fire helicopter from somewhere like Italy, where they are a little bit more used to having fires. So I guess that was just a sort of, for me personally, I sort of think, okay, well that's maybe a little bit out of the range of normal to sort of think about what's been happening. Okay, and then last year as well, there was a massive heat wave where really we had all-time heat records pretty much everywhere, picking up. So we'll see what happens this summer. There's an interesting concept which is known as climate departure. I always find this a bit of a tongue twister to explain, but essentially the idea is there is a point in time where effectively the old climate gets left behind, and so I believe it's the coldest day is now pretty much where the hottest day-to-day is when you're in this new climate. And this was made, I think it was 2013, so it might be a little bit out of date, but you can see certainly along the equator, as you would expect, the hottest part of the planet, some of these kicking in pretty early, like Kingston, 2023. So London here, we've got 2056 is what they projected. I mean, again, these numbers probably probably just about every bit of science I review on the matter seems to be that when people do the numbers again, it turns out it's even worse. So take that with a pinch of salt. It might be earlier, it probably is earlier. But yeah, it's an interesting concept to think, especially in the context of climate resilience and how we might think about maybe what's coming down the pipe. At what point will the temperature have really shifted almost by an entire standard deviation to a new normal? Okay, so this was Australia this year. I think it was January. They actually had to introduce a new colour for their sort of weather map on the TV. I think that's the purple or maybe the black. It was very hot, and this clicker is not great. Okay, and what we saw is that also led to, for example, a die-off of fish. So it turns out that often when it gets really warm, ends up leading to less oxygen in the water. Can be because things like algae pop up and they're taking more oxygen out. So that was interesting, and then particularly seeing the other side of the world, so over in North America, around about the same time, we had a massive deep freeze, and again they were pretty extreme temperatures. There's some interesting pictures, people sort of freezing spaghetti and things outside, making collages up in the northern hemisphere. And so why was that happening? Well, the polar vortex, which typically essentially sucks the cold air up towards the poles, seemed to destabilise and it sort of fell down, if you like, into the lower regions. So I guess just sort of, again, a bit of a roundup of what's been happening. Perhaps of particular concern, been relatively, certainly in Europe, various different crops reducing by around about 20% in terms of the amount of output last year because of extreme weather. And if you think about, say, the human body, for example, if we go beyond, would it be sort of 37 degrees, 30, I don't know? Yeah, it's 37. 37. So if we go much beyond that, then we get a fever, or the other way, we get hypothermia, and potentially we can die. So most crops will have a temperature band within which they are most productive, and then there'll be a sort of decline, and then you'll get to a point where actually it just doesn't work, and that's why we have different crops in different regions. So again, one of the things we're going to have to be thinking about very carefully, because food is particularly key, is what kind of crops can we grow in a changing environment and climate. So the other is looking at grain production. So since we, Joseph was talking earlier about the agricultural revolution, we are largely a grain-fed species. We cultivate many crops, and we've also seen certainly a decline in productivity in the last year or so. Again, largely because of temperatures. Pretty much, you might have noticed it in different supermarkets, just perhaps a slight change in some of the availability of food over the last 18 months or so. And it'll be very interesting to see what happens this year, depending on what happens with the weather. So you might probably have seen these rather depressing headlines over the last few months. The fact that we've wiped out 80% of animal populations since the 70s, and then also this massive decline in insects as well, which is also very alarming, as insects are pollinators. I think it's, I don't know if it was actually Einstein, but it's attributed to him, but there's this quote about, once the bees go, we're not sort of too long after that.
Populations have 60% of animals.
60%, sorry, what did I say?
80.
80, sorry. Yes. Luckily we're not
60's fine.
Oh, yeah,
When it gets to 80, let's have this meeting.
Yes, exactly. Okay, good. So yeah, that's just a roundup then of some of the news. And then, many of you, I'm sure, will have seen the IPCC report, which came out in October last year, essentially saying, final call to save the world from climate catastrophe, and they put this label of 12 years. As we'll discuss a little bit more later, pretty much everything the IPCC says is kind of on the more optimistic end, So if they're saying we've got 12 years, we probably have less. However many we have, who knows? We'll look at that in a bit more detail. But obviously, this should very much be a wake-up call for us to start taking action. And then, of course, there's this perhaps moral obligation, as the Guardian put it here, of world leaders to do something about it. And I wouldn't say that there's no action taking place, but it's certainly not fast enough with the sense of urgency that is required, and indeed some people seem to be going completely the other way. So I guess part of this interdependence project is to say, well, if that's what they're doing, we don't need to be in that same boat, maybe we can actually do it ourselves, or think about how we can do it ourselves. And probably they'll join us at some point. Okay, so climate change tipping points and exponential change. So this is really looking then a little bit more of the science. So we've just sort of seen, okay, what's been happening over the last 18 months that's looked pretty crazy, let's be honest. So what does this all mean? How can we understand that? Well, one of the things that doesn't really get talked about much in the mainstream scientific community, or sort of what reaches the mainstream media perhaps, although I have seen more of it in recent times, is this idea of exponential change. So change that is increasing with speed over time versus just being a linear change. And so that would be sort of how you would draw it on a diagram. If you look at a stock market and you see this, when it's about to crash, that's typically exponential change. Or if you think about, say, bacteria in a petri dish, you might have a doubling every whatever the period of time, and then maybe a population collapse if they've used all the resources. It's also what happens when you put your microphone too close to the speaker. So if you're on Skype, one of those annoying moments happens. That's exponential change. And what's interesting about exponential change is that human brains don't always process it that well. And the theory there is that we've evolved essentially on a savanna. Typically, rhinos were running at us at, let's say, 10 meters per second or whatever it is. And that would have been more or less a constant. It wasn't doubling, so 10, 20, 40, we probably wouldn't be able to escape if that was the case. So we're not really able to, in terms of how we've evolved, it's not a natural concept to us. So perhaps one to just bear in mind. Okay, so let's just talk a little bit about previous mass extinctions. This is something I didn't really know about until the last year or so when I started researching it. So I think as kids, generally we're brought up to believe that there was this meteor strike, the dinosaurs, they all were wiped out, and that therefore, we need to watch out for meteors, which is true. But it turns out, and don't worry about reading all of this, but there's been 5 documented mass extinctions. And so mass extinction is generally defined as, I think it's 90%, maybe 95% of all life getting wiped out. Essentially, a lot of life. But it might be that some survives, which is perhaps some hope, for a bit of hope. And I've just put on the rightmost column, essentially the kind of main cause. And I invite you, by the way, with all of this, to don't take my word for it, do your own research, come to your own conclusions. It's just trying to sort of frame things a little bit for a discussion. But it turns out that climate change, or climatic change, had an impact, whether it was the cause, or maybe it was the effect after some other process, but there was definitely the markings of some climatic changes in pretty much all of these. And what's interesting in particular is the third one in this list, so the end Permian, is where, so if we just put causes to one side, whatever the cause was, there was an awful lot of methane that was released very rapidly, and that led to a rapid warming. Some of the others actually involve cooling, and so that's not really what's going on now. We're definitely having a warming. I think possibly the other point to just to mention here, and I didn't put a slide in, but what seems to be, we'll kind of come back to it, but there has definitely been an oscillation between different temperature levels on planet Earth. That's certainly something that we've seen over time. So it isn't a new phenomenon that we have these flips from one climate state to another. what is new is that the dominant species on the planet is actually causing it themselves. That never happened before, as far as we know. Maybe in years we'll find out that the elephants were running around with guzzling Humvees or something. Okay, so just a few charts then. Often, when I look at the data that is presented, say, in the mainstream media, we get a chart that is just sort of the last few years, and it tends to look like a linear change, like a straight line, more or less. But then when you zoom out to this website, I invite you to have a look at it. It's called methanelevels.org. It's free. And they go back as far as they can go, and they've got methane and the other greenhouse gases. And what happens when you look at this time scale is that it does start to look a lot more like we've hit an exponential change. And I think what's particularly interesting, well, I guess a general point would be that this level of abstraction can often help us situate where we were, just a little bit like that story we just told. But also, I think in terms of, part of the discussion today is sort of how do we process this information. And as I mentioned when I introduced myself, I've spent the last 10 years fighting the good fight in terms of climate mitigation. But actually, when you look at it, maybe when we discovered fire, that might have been the start of this journey, or maybe that's not quite as far back for that one. But certainly, if you look at when the Industrial Revolution began, that's definitely where the uptick comes. So at least we can perhaps let ourselves off a little bit that we weren't maybe the driving generation. Not equally to blame those that came before us necessarily. They didn't really know that they were going to do this, I don't think. Maybe the gentleman who discovered the greenhouse effect for the first time, he did try to sound the alarm, but unsurprisingly, those who were making a lot of money out of coal wouldn't really want to promote that idea. Okay, so that's carbon dioxide. This is again just giving a little bit more, maybe this is actually more in line with humans and how long we've been around. So depending on which variety of Homo sapiens or other Homo erectus or whatever it might be, 200,000 years to 100,000 years, I think Harari in his book Sapiens talks about 140,000 years. So what you can see is that humanity has thus far evolved and grown up in a relatively stable temperature band. And then obviously you can see at the end there, so 2017 average, 405 parts per million. We've now just surpassed 415. We don't have the average data necessarily for that year, but yeah, on this chart here. Anyway, you can see that it's certainly out of kilter with what came before. So James Hansen, widely regarded as the godfather of climate science, he was the first person to get up in front of Congress in the US and to essentially, again, sound the alarm on climate change and its impacts. So he talks about essentially 350 parts per million being that safe band. And so there's an organisation that you may be familiar with called 350.org, that's why. And the point here to mention is that the idea of 2 degrees is, I'm afraid, a complete misnomer, and no really sensible scientist would really have recommended that. Indeed, James Hansen doesn't talk about 2 degrees, he talks about 350 parts per million, which, of course, is driving the temperature. Now, unfortunately, the 2 degrees target that's come out of the Paris Agreement, or indeed the 1.5 degrees, is very much a result of a political process. What can we actually potentially do without upsetting too many people, rather than grounded in science? Okay, so this is looking then at methane, which, as we saw earlier, is another greenhouse gas that's actually more potent. And again, we see a similar trajectory and process of an uptick since essentially the Industrial Revolution. We'll share all these slides with you so you can go into more detail and look at them yourselves. So yeah, just to kind of recap there then. So methane in particular is of great concern, partly because there's a lot of it under the oceans, frozen or either trapped in under the oceans or frozen in things like permafrost. And although over 100 years it might be 28 times more potent, actually over a shorter time period it's quite considerably more. So whether that be 3 times more, 4 times more, whatever it might be. But the point there being that we could experience a very rapid warming in a very short space of time if we were to release a lot of methane. And it would appear that that is what happened when we had a previous mass extinction. There's various different reports out there. I think, for me personally, in trying to understand how quickly these things could happen, that always seems to be an important thing to me personally. Don't quote me on this, but what I've read seems to suggest anywhere between 2 and 10 years is the minimum, the fastest it could go. It could, of course, be a lot slower than that. But I guess when I'm thinking about this, I'm almost thinking about it from a sort of risk management point of view of, well, I'd rather plan for the worst and hope for the best than plan for the best and see what happens. That just doesn't seem like the best precautionary principle approach. But as I say, go and check these things out yourself. I can give you some references and things to take a look at. Okay, so let's just talk a little bit more about methane. There is an awful lot of methane, as I just mentioned, trapped under the ocean and then also in permafrost. In particular, often referenced is the Siberian Arctic shelf, which has apparently 2,000 billion tons of methane, which is a lot. If you have a look at the World Oceanic Review website, it seems to suggest that actually there's methane dotted around pretty much everywhere, and that if it were all released, which I think is unlikely, but if it were, then you're looking at between 100 and 500 times the same impact as all of the fossil fuels that we've burnt so far. So, in the sort of Armageddon scenario, it's most likely as a result of all the methane being released. And if you ever hear about people talking about a Venus effect, so Earth becoming like Venus, where Dr. James Hansen has done quite a lot of work on that, where he's looking at his understanding of how that happened. And pretty sure he had it peer reviewed by a lot of other people. But essentially, it's a runaway greenhouse effect that has occurred on Venus.
How come is the methane stuck then?
That, I'm afraid, is above my pay grade of knowledge in the science world. Probably better asked a geologist.
But is it us? Does it end up there because of our production?
I don't believe that we put it
would
there.
have been when it froze originally.
Like a long time ago. But if it melts, that's how it will be released.
It's caused by breaking down of organic matter. That's why it's a massive byproduct from agriculture.
Okay.
So it's like actually from old, like similar to gas and oil. It's the result of degraded animal and plant matter, and it gets trapped just on layers and layers of sediment, and trapped in ice cores when things freeze.
Yeah, maybe just to mention as well, so I mean, it's not just methane that is say being released from the Arctic or wherever. It's also so cattle produces methane. I mean that is us. We're definitely doing that, and then also climatic changes that might mean that it would be released from things like sort of like bogs or like lakes that might have it. So there was a report that came out about 10 days ago that unfortunately said that methane was increasing, and it would appear from what they were suggesting in this report was it was actually around the tropics or the equator band, so not from here, and they put that down to various different lakes where the climatic changes were releasing it.
So just take a nice deep breath.
The landfills also release methane as well, right?
Should we just have a 2-minute break of just standing up for a second, just maybe just shaking it out a little bit? Like, actually, what we're doing. If you're watching at home, I invite you to do some star jumps. Can we demonstrate? Alright, well, we're all sufficiently stretched. We shall continue. Alright, yeah, let's move on.
So the east side of your ice itself, are they clay flakes or is that like trapped in the ice itself?
Again, I'm not entirely sure. I think that I know the under the ocean is the one you just mentioned, but I'm not entirely sure. Yeah, that's to check that.
What's this word?
There's a layer of frozen ice, obviously. So it's all there because organic materials do the same.
Let's check this out. Yeah. Alright, so this is then looking at just temperature. So you've probably seen this before, it's sort of the famous hockey stick. But again, it just sort of helps when you zoom out to a larger scale, just to have a sense of where things are at. So I believe, just to sort of see looking at this, but we're somewhere around, what does this one say, that was 1.11. So yeah, we're somewhere in the sort of 1.1 to 1.2 degrees above pre-industrial levels.
If you want to mark on the screen, that's a little later.
Okay, thanks. And then so the Met Office actually produced a report that came out the other day that was on the BBC website, and it said that although it might not be, it might just be a temporary sort of blip, and you can sort of see this on the chart down here, that we can actually reach 1.5 degrees within 5 years, which is certainly interesting when you think about the context of Paris, 2 degrees, and also the fact that ultimately the reason we have had this idea of 2 degrees, 1.5, or really any desire to limit it, is that we've always been worried that we might trip runaway climate change, where the feedback loops kick in and we lead to more exponential change. This hasn't been widely talked about, I haven't really seen it anywhere else, but it's a pretty significant thing that has been announced there. That we, just 5 years, we might be at that point that has been for so long talked about as the point beyond which we should not go. Although arguably, if we think back to what James Hansen has been saying, 350 parts per million being the safe level, well, we're quite considerably above that. I actually heard Paul Hawken talking about this on an interview. So he's the person who did the Drawdown project. And he actually said, which I hadn't really thought about before, but it makes a lot of sense, is that 415 parts per million, okay, great, but when you actually add up all the other greenhouse gases, you're looking at more like 480 or something like that, which is even more concerning. The other, maybe just we'll come back to actually, I guess the other point just to say is that the last time we were at 415 parts per million, was around about 4 million years ago, and the temperature was 2 to 3 degrees higher than it was today, and the sea levels, depending on the sources, somewhere between 20 to 40 meters higher than today. And the reason that we're not necessarily seeing that now is because there's a time lag. These things, you're talking about an entire planet rejigging itself, and so that may well be what we might have locked in already, if history is to be any guide. I'm not saying that's what's going to happen, I don't know. I'm just suggesting what has happened before. One other point to note within that is that the oceans absorb an awful lot of heat, and it would appear actually they did a few reports in the last year that most of the energy has been absorbed by the oceans. But that doesn't mean that it won't dissipate in the future, out from the oceans. Okay, so this one then looking at sea level change, and I believe the most recent data on sea level change is also suggesting that has, if it was a linear curve, it's definitely, or it's, the latest data suggests it's more of an exponential trend. I think we've had about 20 centimeters of sea level rise since the more or less Industrial Revolution. Again, generally speaking, the information, pretty much every time you read something about this, it's worse than what you read before. So if you are thinking ahead to where I want to live, I would suggest make it above, ideally 50 meters above sea level. So, I mean, if you're going to make the effort of moving somewhere, just don't do it, 10 meters above sea level, because that would be annoying. And your friends and family won't thank you. Okay. Alright, so let's talk a little bit about why the Arctic matters so much. Again, this isn't really, personally, I didn't really understand this that well until recently. I understood that there were climate feedback loops, but I didn't really understand the specifics. And it's actually very simple. So we talked earlier about the greenhouse effects, the sun's rays coming in and essentially hitting the Earth. And the question then is, how much of those rays and how much of that energy bounces back out into space? If you think about somebody with a mirror and the reflection, how much of that energy is going back out? So when we have ocean or land, that absorbs far more of that heat. And if you think about it, when you go to, say, hotter countries, but even here, often you have water heating tanks that are black, or if you just wear a black t-shirt or a white t-shirt, you can have a very big difference. And so the Arctic, and indeed the poles in general, the ice caps, serve this purpose of they're not there just to serve that purpose, but they have that effect of reflecting the sun's rays back out into space. So the more we lose Arctic ice cover, the less of this effect is happening, and the warmer it is getting. And that essentially is the essence of these feedback loops. There are others, but I would say that's probably the simplest one for us to really understand, and it's likely to be a driver of the others. So this is essentially a model that is looking at I think it works on screen. Okay, so it's looking at so the black is observed data, so what they've actually measured. The red is an exponential trend curve that is, fitted to the data. So it's kind of a mixture of observed, but then some modelling. And then you've got all these different lines over here, which are different people's models. And essentially what this is saying is the decline of the Arctic ice and where we think it's going to go within the next, this is going up to 2025, in fact just a little bit less. Of course they could be wrong, and it could be that it happens later, but it could well be that we have an Arctic that is ice-free, I believe in the summer. It might, I think in the winter is a slightly different story, and that's very soon, as you can probably understand. And some of these models are saying even sooner than that. I guess this thing that I'd invite you to think about is exponential change, things going very rapidly. That may well be the trend that we're in now, and that's actually what this red line is trying to show there. So we've probably seen before images of the Arctic and the sea ice disappearing. So that's essentially over the last 40 years or so, we've lost about 50%. That's obviously a big concern. A couple of charts then from the last year. So this was the Arctic. I think this for me is when I thought, oh dear, maybe we've tripped runaway climate change. It was around about the time last year, I think, when we were having the beast from the east cold spell, which, if you remember the polar vortex diagram earlier, essentially the cold weather coming down to lower latitudes and actually being very hot at the Arctic, at the poles. And this was essentially, I think it was 35 degrees, I can't remember if that was Fahrenheit or the other one, but essentially, I mean, you can see here, it was beyond what you particularly, I mean, you can call that an anomaly, but it's a particularly alarming anomaly. So that was the Arctic temperature, and then this one was looking at the sea ice in the Bering Sea, which is pretty near to that Siberian diagram we saw earlier. So what I would argue is that these are the kinds of data points that are consistent with us having triggered runaway climate change. This is what you would expect to see. Okay, so I mentioned earlier that the Earth has been here before, effectively. So this is a diagram from an academic paper looking at this idea of these changing states. So a glacial situation to stabilised to a hothouse Earth. I find this diagram personally a little bit difficult, so I'm going to show you another one in a moment that's maybe clearer. But essentially what it's saying is that the Earth has traversed different paths along this over time, and that stabilised Earth is where humanity has grown up. Maybe we haven't grown up fast enough, and that actually, we could go into a hothouse state. So this is it in a slightly different way of thinking about it. It looks like as a cycle and an elliptic. So stabilised Earth is where we are, and if we have runaway, then we could go to a hothouse Earth state, which would mean more sea level, higher temperature, or it could come back the other way, which would be more of a sort of ice age situation.
In which scenario could it come the other way?
In one where, for whatever reason, we have a massive cooling. I mean, it's pretty unlikely right now. It's not like that's likely trajectory from where we are, but that's sort of the other extreme.
Yeah.
If we have loads of organic matter, then it puts loads of oxygen in the air, and that has the opposite effect of CO2, reduces CO2 consumption concentration, because there's more plants and animals absorbing CO2, and oxygen has the opposite effect, so you would get a cooling effect, and it kind of happens. Maybe that's even how we get seasonal change.
So the first trees from the story, when they were storing in the carbon, and weren't being able to be broken down, that's where that was going. And life managed to step back.
Yeah, so it's like carbon, sorry, what was it? It's like carbon, you've heard of carbon capture? I think that's the idea is that you'd have lots and lots of plants and organic matter that would absorb the CO2, capture it and keep it out of the atmosphere. But you have to be careful, because if you just grow loads and loads and loads of a single species of something, that leads to other problems. So maybe what would be better is carbon capture by rewilding. So rewilding, so like taking land and allowing it to be reclaimed by nature in a way that is kind of more natural. So
All right, well, Karen, we're nearly at the end now. Okay, so just moving on then to other feedback mechanisms. I mentioned the Arctic is probably the simplest to understand. I think there are actually something like 60 that are understood, but here are the main ones. And so, obviously we have the Arctic, but we also have the Antarctic. Unfortunately, there's more data coming out that's melting faster than they thought, which is pretty typical of what we see. We also have the Amazon rainforest, which is often thought about as the planet's lungs. It's breathing in all that oxygen, or CO2. We've got the Gulf Stream, so the thermohaline circulation current. Often the idea that actually we have more ice melting, then changing the composition in the ocean, actually having the effect of slowing down that Gulf Stream, which is actually potentially makes Britain a good place to be if temperatures do spiral. If you want a small silver lining. So at the moment we're kept artificially warm by the Gulf Stream. So if that shuts off, but then temperatures go up, maybe for a while we won't be as badly affected as other places, but depending on how far things spiral, it could be pretty bad here too. I won't go into all of those, but just to sort of say there are many interlinked or interdependent even feedback mechanisms. So last point then really on the IPCC, which is the body that for a long time, that's where I went to get my news. And then I've kind of started to understand a little bit better that maybe they're not the most reliable game in town. And I think so this is a little bit out of date, but it's essentially showing the projections versus the observations. Now, the IPCC has many scientists in it, but it's largely a political process. And if you're going for the peer-reviewed of the peer-reviewed of the peer-reviewed, so trying to be that gold standard, with data that's changing very dynamically, it's difficult to be up to date if your process takes 3 years, and also when you've got a lot of political pressure on that process. So I guess what I would say is it's not to say all the scientists in there are not credible, they are, but the process itself is perhaps leading to slightly more optimistic data. All right, so before we kind of put everyone into groups and let you process this a little bit on your own, I guess what I wanted to just talk about is this overcoming the urge to look away, because it's certainly something I've experienced myself, where, as I say, so my journey, I've been working in this space for a very long time, and I even wrote a book back in 2011 about climate change and talked about all this stuff. But then I busied myself trying to do something about it, or what I thought was doing something about it. And when out of the corner of my eye on my Facebook feed, I started seeing these bits of this kind of information about a year and a half ago. It took me a good 9 months to actually go and find some other people to talk to about it and sort of help process that. So it's a journey, and invite you to be kind to yourselves along it. You might not ingest it all in one go, but here's just perhaps a little model or mental map for thinking about how to process that information. So I'm calling this acceptance versus denial. Denial feels maybe like a bit of a strong word, but we'll leave it there. So let's say, as you're doing today, you're reviewing this information, and there's other information that I suspect you'll probably go and look up yourselves. And there's almost, I would say, there's almost a binary choice. Do you accept what is being explained and process it, and then perhaps forge your way forward, or do you perhaps deny it and say, well, maybe there's one little bit here that's wrong, so I'm going to ignore it, or however you might decide to deny it. But over time, as the evidence becomes increasingly available, when you can see it outside the window, when other people start talking about it more and more, when that Overton window within the when it becomes mainstream, I think that will become ultimately impossible. And so you're ultimately going to be in this having to accept it place anyway. And the question really is, do you do that at a point along that journey that enables you more time for forward planning and more time to help mitigate suffering in society, whether that be your own personal suffering, those around you, however you want to think about it? Or do you deny it and put it back in the box, which gives little or no time for forward planning and doesn't really help to mitigate risk and suffering? And that's kind of how I think about it. So I would say that gives you then a few different options if you come over to the acceptance point. So one is to move to a conscious state of denial, and I respect that. I understand why you might do it. It's a bit like, in the Matrix when you get the red pill and the blue pill. Plug me back in. Sorry if I've unplugged you and you didn't want to be unplugged. Give up, retreat, don't help your global or local community. That is an option as well. But what I would say, and this is really what this interdependence movement and community is about, is to say, well, look, what's actually the optimum response here? This is obviously pretty tough stuff to deal with. What I'd say is to take action to help your global and local community to prepare for the future impacts, and also to take action that mitigates harm and suffering. I think, obviously everyone has different ideas of morality, and many religions talk about it slightly different ways. But there's this common theme that we should be really trying to help each other and minimise suffering. I think that's what most of what we would consider civilised society to be. And maybe that's going to get a little bit tested, but if we want to be resilient in that respect, I think that's a compass forward. All right, so Joseph, do you want to introduce this bit?
So we're going to have 2 little sections to this break. The first part is we're just going to ask you to go